In this demonstration, I would like to develop the characteristics of the Poisson distribution. We started with the properties of binomial distribution and with the inspection and um, the numerical values. We found that if we add up all the probabilities for x, where x in a discrete distribution varies from 0 to the n number of trials, so it was equal to 1. And we know that it was difficult to establish by using the analytical expression of binomial distribution. However, it is easier in case of the uh, Poisson distribution expression uh, that we developed earlier. So, so when x is equal to x, about a mean value, it is e raised to the power minus mu, and then mu raised to the power x over x factorial. So if we add up all the probabilities of the events, then this will lead to 1. So let's perform this calculation for this expression. So this expression, okay. So the normalization property with respect to Poisson distribution. So x values are from 0, 1, 2, and so on up to n. So the sum of all possible event probabilities. So x should vary from 0 to n. So I can write it is e raised to power minus mu, mu raised to the power x over x factorial. So summation is understood. Okay, x to the n. So I can eliminate e raised to power minus mu out, and then with the value 0, it becomes 0 over 0 factorial. So then plus mu over 1 factorial, then plus mu squared by 2 factorial, and so on up to the value n. And for a very large value of n factorial. So this expression from calculus is approximately equal to e raised to the power mu. So the actual expression requires the infinite terms to be calculated. So this is going to be the approximation, and then therefore it will become equal to 1. So something which was a bit hard to see from the analytical expression of binomial distribution. So it is relatively easier to see in the case of Poisson distribution. So then let's look for the second property, which is the mean value. So the mean value of the distribution, mean value is represented by the expected value of x, and it is the first order moment. So the expression for this one, e of x, is a summation of events with the x values times the corresponding the probability value, where x varies from 0 to n. So this will be likewise x 0 to n, x e raised to the power minus mu, and mu raised to the power x, and over x factorial. So this is what required. So again, we can get this e raised power mu outside and then write this one for a value 0, then for a value 1, then mu raised to the power 1 or 1 factorial plus mu raised to the power 2 times 2, well, 2 from the x value and mu square from this mu raised to the power x, and over 2 factorial plus 3 mu cubed by 3 factorial, and so on and so forth up to the last one. So which is going to be in this case n times mu raised to the power n over n factorial. So we can see here that the uh, this will reduce this one to uh, one number less factorial. So this will be then reduced to n minus 1 factorial. So we will have e raised to the power minus mu. We can get this mu outside, and then the remaining expression is again e raised to the power mu, and so on, so forth to mu n minus 1 over n minus 1 factorial. So for large values of n, we can see that it is approximately equal to e raised to the power mu, and which reduces this one to mu value, which is which was defined from n times p. So Poisson distribution and the binomial distribution, their mean value can be calculated by the number of trials and the probability of success in one trial. So this is also going to be valid for the mu value when it is defined for the characteristic Poisson distribution, where we know that it is equal to mu is equal to the lambda value, which is the probability rate for an interval, and times the t value, which is the fixed interval in which the probabilities are to be estimated. Okay. Then for the next property, uh, the next statistical metric is the variance value. So for variance value, which is the central second moment, so which is x minus mu n squared. So square due to the second order, and minus mu is that it is moment is calculated about the mean value. So the expression can be established, but it is not that straightforward as the case of probability and the mean value. So we use the same result which was confirmed numerically for binomial distribution. So it is going to prevail all the well, it is going to prevail for the Poisson distribution. So it was the square root of, well, it was square of, well, it was, sorry, npq. So which was equal, yeah, this was equal to npq in case of Poisson distribution. So we say np times 1 minus p, and to the approximation, if we look for the smaller values of p, then the squares are going to be much smaller. So we say that they are approximately equal to 0. So this will be np, or the mu value. And the fourth metric is the nice one, the standard deviation. So standard deviation sigma will be the square root of mu. This is a very nice character of the Poisson distribution, that its sigma value is the square root of mu value. So which is useful with respect to the counting experiments, that we can estimate the error or standard deviation in one observation value by calculating its square root. So it is of importance in the counting experiments which are in the spectroscopy and the radiation counting experiments. So this is about the properties of the Poisson distribution. So the estimation of standard deviation is also important to see in the context of hypothesis testing, that which of the confidence intervals are considered. Sometimes to one standard deviation, the confidence intervals are considered. Sometimes the up to two standard deviations, and in some cases up to three standard deviation confidence intervals are considered about the mean value. So, which is the topic in the statistical inference. Uh, so, we can see that one with the help of an example. For example, we were talking about the defective component probability 2.1, and the sample size is around 20. So we see that the mu value is 2. So the majority of the probabilities are distributed about the mean value. So this is the mean value, and we see, as if we look for the probabilities to two digits, so they are distributed about the central value 2. And if we see for the sigma, well, again I should insert it from the symbols. So sigma symbol. Okay, so it is should be among the Greek letters. Yes, alpha, beta. This is delta, and somewhere sigma. Oh yes, I got it. Sigma value. So from the Poisson approximation, I can say that it should be the square root of this value. So 1.414. So roughly to two value. So if I calculate the probabilities uh, to about 2 units uh, from the mean value, So let's see this number. So sum from here. So so it is about 95 percent, or to 96%. Oh, this is very nice. Generally, in several cases, well, it is highly dependent upon the cases to be considered. So we consider the 95% confidence interval. So the 95% of the probabilities, they belong to the events in which the x values are from 0 to 4, and the rest of the uh, about less than 5% probability is distributed among the all other events. So significant events among all those 21 events, so from 0 to 20, so only the first five events, they are of significant importance. That is the context of hypothesis testing. We will explore that one later on in that case. So let's stop at this point for this video.